buenas tardes. Bienvenidos a esta sesión del seminario Súmate. En vista de que nuestro expositor esta vez entiende el español, pero no habla bien el español, según me dijeron, voy a hacer mi mejor intento por hablar en inglés. So welcome to this particular, very special session of Súmate. And as you know, our speaker today is Professor Cláudia, and she is doing an academic visit with our colleague César, and I don't know what else to say, so I'm just gonna.
Thank you.
Go ahead.
Thank you a lot, Roberto. Thank you, all of you, to be here in this break week, isn't it? It's really nice. I would like to start to thank a lot César, because he's the reason I'm here. Actually, he made all the paperwork, helped me with all of this, and to be here, I have been having wonderful days. And in particular, of course, I'm here because of the program of UNAM that is funding my visit. So thank you very much, UNAM. It's an amazing university. I'm very grateful for this opportunity. So this work is, So this, we are going to see the complexity of the minimum cost flow, decomposition problem on uncolored networks. I will explain every term in the continuation. And this is a joint work with Cláudia Carvalho, Jonas Costa, and Ana Carolina Maia. So Ana Carolina is my colleague at the Federal University of Ceará. Cláudio and Jonas, they were Ph.D. students of us. And this work I'm present here was as one part of the thesis of Cláudia, actually. So I'm start to define everything. In particular, I'm going to define what is a network, and which is our object of work here. And a network will be only a digraph, okay, with a capacity function on its arcs. That's all. And special vertices S and T. And as usual, we call N the number of vertices and M the number of arcs. So this is a network for us. And we are interested in this thing called flow in the network. Maybe you have already heard about this term. So a flow is a function, actually, also in the arcs of the digraph, but with the special requirement that a flow cannot be greater than the capacity of the arc. So the idea is you are sending things through the arcs. And so the flow you are sending, or flow anything you want, cannot be greater than the capacity of the arc. And we have our special vertex S and T. And another thing that is every vertex other than S and T has to be in the path from S to T. Otherwise, it won't be. They will be useful for the flow. And we are going to say that a flow is uniform if all the values of the flow are equal, except those ones which are zero. So in my notation, the first number is the flow, and the second number is the capacity of the arc, okay? So here we have a flow, which is uniform because every positive number is equal to 2, and some of the arcs have zero flow. That's not a problem. But actually, we are not interested in any flow, but in ST flow. So this is really special. So I'm interested in how much flow actually I can send from S to T, and I have to attain another condition, that is my function has to be conservative. I mean, I have to, the property of conservation has to be satisfied, which means that all the vertices less S and T, every flow that a vertex receives from his neighbors has to be sent to his out neighbors. So let us look D. So D is receiving 2 units of flow from here, 0 from this one. So it has to spend 2 units of flow. So he is doing this, one here and here, that's okay. It has to be satisfied for every vertex except S and T. And why? Because S, we expect S to give flow and T to receive flows. S is the source and the T will be the sink. And actually the value of a flow will be determined by how the amount of flow leaving S, which would be, because of the conservation, equal to the amount of flow arriving in T. And this minus because of the formula of balance. I mean, the balance of each vertex will be the flow it sends less the flow it receives, okay? So then the idea is, if I have a network, how much flow can S send to T? This is the question. It was a main question several decades ago, and that it's proven, and actually it's not a very hard problem to compute the maximum flow. Actually, after Gordon Fuchs gave us the result that, well, they proved a very nice minimax theorem. They proved that the value of the max flow is equal to the value of the minimum cut of the network. And because of this result and some improvements, we have a polynomial time algorithm to solve this problem. This is nice. So this was not, but there an observation about this algorithm. It was like this. So you pick any path from S to T, and you see how much flow I can send along this path. So kind of those algorithms that take path by path from the flow to build a flow, the maximum flow. So you are interested in this thing, the path flow. This definition is a path that you want it be from S to T, which all have the same amount of flow. So here, for example, in this blue guy, this blue path will be a path of a path flow, because every flow here has value 2. And we are also interested in cycle flow, would be, I mean, this apparently useless thing that would be a flow along a path, a cycle of the network. And again, I want every arc in the cycle have the same value of flow. We are interested in this because of, as well, this flow decomposition theorem for the Fuchs at the same time. So they proved that every flow like this, every flow actually can be decomposed in at most n plus n path flows or cycle flows in this type. So it's polynomial. But actually, if I want a nice algorithm, I want to have a minimum number of paths as possible, isn't it? To send things and arrive in this maximum flow. This is a natural idea as well. And then, and this is why you have this definition here. We are going to say that flow, SCT flow, is case-splitable if it can be decomposed in path flows of x1 to xk, such that the sum of all the values in this path is equal to x. So I can split my flow in these paths and take one by one and send the flow, etc. And then we can say, no, so cycles are useless. We can think about this because cycles are doing nothing. But actually not, because, so another observation I will do here is, from now, I'm not interested anymore in the capacities because I have a flow. So from now, the only thing that interests me is the flow. And I want to split this flow as I can, okay? So forget about the capacities. The thing was already solved. And cycles can have an impact in the number of the paths if I want to minimize it. For example, here in this network, I have the flow, which is value 3, can be split in this path and this one, isn't it? So it's nice, 2 paths. But if I decide to remove, oh, have you seen the two paths or not? But I have the cycle, so you can say, oh, this cycle is not a cycle flow, but as a cycle, a direct cycle, and maybe I can remove it and have to analyze. I will have a smallest network to analyze. But actually, if I remove this cycle, then I can't have three paths anymore. I will need three paths. I will need this one and send one unit of flow. I will have this one send another unit of flow, and the third unit of flow will be sent by this one. So I have to keep the cycles to have to compute the smallest number of paths that can spin a flow. And this is the problem. We know that every flow is unsplittable by atoms. And of course, we are interested in values so k is smaller than n. And people have been studying this problem. The first one is, okay, I fix the number of paths and I say how much flow you can send only using this amount of paths. And the second problem is the problem that we are interested in is, you give me a flow and I will find the smallest number, the smallest k such that k is, such the flow is k split. This is the problem we are interested in. And so this problem can be stated like this. We have a network and that's the flow. So the flow, I don't have to compute it, it's given. And k, an integer, and I ask if the flow is k split. And it turns out that this problem is, I do something, oh, sorry. It turns out this problem is NP complete, even on DAGs. DAGs, remember, are the direct acyclic digraphs. We don't have a directed cycle. We can have cycles on the underground, I mean, graph, but not in, but they will be all not directed ones. And this was proved, oh, shoot. So, and then it was proved that it's incomplete DAGs. And this was I will explain quickly this reduction. So for because of the three partition problem, it was very beautiful. In this three partition problem, we have a set with the three R elements, a function that assigns to every element a value, a natural T, and we want that the value of each element is between T/4 and T/2. And we also want, if I sum all the values, have R times T would be the result of the sum, okay? And the question is, can this set S be partitioned in R sets with three elements each, such that the sum of each three is exactly equal to T? This is the question. And then we have done, actually, they proposed this reduction. So this reduction is very simple one. So I will put one vertex for each element of my set, and the value, the flow in the arcs, these two arcs, this P2 will be the value of AI for every path here. And I will put extra R elements represent each set that I want to find. And the value of the flow here, I put T. Every arc here is flow equal to T. Of course, it will be a flow because this sum is R times T, and this sum will be R times T as well. This is nice. And it's easy to see that if I can decompose this flow in 3R paths, I have a solution for the two partition. And the other way as well. Okay, I'm giving you this reduction because it's funny. When we start to study these problems, just to encourage you students, we proved this using the same reduction. And then, okay, let's one of the students say, okay, let's say if it has been proved already. And it was proved with using signal reduction. See how the ideas kind of, you know, we could easily, if we have to check the things actually, because more than this, people have the same ideas as you and you cannot be met with this. And then, this problem, we know that is hard, but actually it's really hard because even in the case only we have, because here, you know, I have lots of values of flow, of flow in the arcs, isn't it? I have lots of values, as many values as the set S, but Hartmann and others prove that only if I have 1, 2, and 4, if they are the only values of flow on my graph, this problem remains incomplete. And actually, they prove also that there is a case where it is polynomial, which is I have only 2 values and one divides the other. This is, and then okay, but it would be, what are you going to do? Actually, we were not interested in this problem, really. We were interested in work on arc-colored networks. And I will define for you. So an arc-colored network will be, I mean, the same thing we had before, but now we assign to each arc of the digraph a color. It's not a proper edge color, it's any color. You can use 2 colors, 3, or 1 color. They can be monochromatic, you know. And we'd say that any C of D will be the number of colors I'm using. And we say as well that span C of D will be the number of components in the subdigraph induced by color C, by the arcs colored C. And we have, and people before us, they were studying network, arc-colored networks, and they were interested in these 2 problems. First of all, they were asking what will be the, it's possible to find the maximum flow with the fewest colors, because you have several solutions for max. It was not one solution. They were looking for a maximum solution with the fewest number of colors. And the other problem was, given S and T, can I find a path from S to T with the fewest number of colors? So in the first case, okay, we're interested in the flow, but in the second case, actually it can apply to an arc-colored graph, isn't it? And then the results are not very, I mean, good. So this problem to find the maximum flow is incomplete. This is a result from Granata and other people. And actually find a path with the minimum number of colors between 2 vertices is also incomplete. So it's funny because these 2 problems are very simple problems in monochromatic networks, isn't it? And it turns, both of them are difficult here. But we are, recall that we are interested in split our flow. And then we are, okay, let us define a function, custom of which be the splittable. It's the number of, we had to relate the number of paths and the number of colors in some way. And then we define this problem. It's the minimum colored flow decomposition. So we determine for each path its number of colors, okay? And then I will say a cost of a decomposition will be the sum of the number of colors of each path. So if I have a path that uses 3 colors, I sum 3, another that uses 1, I sum 1, and so on. And I'll be interested in find a decomposition in paths that minimize this sum, which would be the number of colors, but 1 by 1, used in each one of them. And just to show you that actually these 2 problems are different, which problems? That, I mean, the case splittable problem that we saw before in this one is, it's easy to see in this graph. In this graph, in this network, If you look at here, I'm saying 10 units of flow from S to T. So I will divide like this. I will take this path, which is monochromatic and has value 4, okay? And then I will take this monochromatic path, blue, and I will need 6 of them to conclude this. So with 7 paths, I decompose this flow, and the cost of it will be 7, because each of the paths will be monochromatic, okay? But actually, this flow can be decomposed in 6 paths if I'm not worried about the number of colors. So I will start. I don't know if you can see. I will start with this path, but I won't take it with 4 units. I will take it with 2 units and 1 color, and then so I will let this network. And I will take the path, this path I'm showing here, which is bichromatic, and I will send 2 units of flow. And I will do this, I will take this other one, as you have seen, 2 value 2 and 2 colors. And I will do this as long as I can, take a path with 2 colors and 2 units of flow. And I will let with these guys, and so I have 2 of them, bichromatic as well, send each one 1 unit of flow, as you can see in this one. And okay, I have split my flow, but I had 6 paths. It's nice, but the number of colors was 11, so it can be really different. And so this is also, okay, we find an interesting problem. We were happy with this. But okay, so this is the problem. And then decision version. We are given a K, an uncolored network, and you ask if it can be decomposed in any number of paths, but with cost must K. And actually prove that this problem is NP complete, and even the flow is uniform. And why I'm saying this? Because actually, I didn't tell you, but if the flow is uniform in the other problem, it's very easy. No problem at all, we don't care. But here, even if the flow is uniform, it's NP complete. And even I may have only 3 colors. Actually, the reduction was we found was from this problem, the reduction to weak leakage. And this problem is, let me state, you are given a graph only and 2 pairs of vertices. And you want to know if there are 2 paths joining E1 to V1 and U2 to V2, which are arc disjoint. This is the thing. And so in this case, actually have the answer will be yes, we have this path and in this path. And then you notice that they can share a vertex. They are arc disjoint, but not vertex disjoint. This is why we call this problem weak. This is the weak version of the 2-leakage problem, where we are required to have vertices and edges be disjoint, okay? And then so our reduction was like this. So I take my graph that I want to find if answer yes or no for the 2 weak linkage problem. And of course, I have to transform this in a network and a flow, and I have to define a flow in it. And then I will I have to have this SAT normal. And then I start to, and this you are going to see the function of this additional vertices, and then I will add this edge. So I will maintain all this color black, and I will add red from U2 and red V2T, blue from S to V1 and from V1 to T. And just looking at this, if I have 2 bichromatic paths from S to T, since it will be uniform, the flow will be uniform, so I don't have the right to use the same edge twice, the same arc twice. The answer of the other problem will be yes, that's a bit. But okay, it'd be nice, but I have to transform this in a flow. Then I add lots of, I have m edges here. I add m minus 2 edges from blue, from S to S1, black from S to S2. And I actually, you remember that I don't know if I told you, but if the flow is uniform, the in degree of any vertex has to be equal to the out degree of its vertex, because the same flow that arrives in one vertex has to go out. And then these red edges from S2 to all the vertices have the intention to make the out degree be nice. I will look every out degree, and I will compute things. I will complete with red edges if needed. And I will put, so I repeat here the same structure for m minus 2 edge, m minus 2. And these blue edges will to balance the in degree now. So now I have really a network and a flow. Which value of lambda? No matters. Any value of man. They are the same, okay? So look that I have 3 colors. So I can expect that at most the cost of my thing will be, I have m paths. I have m paths. The maximum cost will be 3 times n. And then if I actually have 2 bichromaric paths here, I can have a less cost, a cost smaller than this. So I ask if I have, if I can split this flow with this cost, 3 times n minus 2. To do this, I have to find 2 disjoint paths. From S to T, only using this area, this black edge, and one blue and another red, okay? Like this, for example. I don't know if you can see, this will be one, and the other one will be the second one. And you can check that it's easy to see that the same on the contrary wall, so would be nice. But the thing is that, so okay, so you know this weak two linkage problem, it is polynomial if the graph is direct and acyclic, there's a DAG. So we think, oh, maybe in our case, it's also nice. It will be polynomial. If I have a uniform network and no directed cycles, it would be polynomial maybe for us. And actually not. Actually prove that it's NP complete even for acyclic networks with at least 5 colors. I have to have at least 5 colors. My reduction needed at least 5 colors. And we made the reduction for this problem from 1 in 3 sat. In this problem, you know, it's the same of 3 sat, almost the same. So each clause has 3 literals. But we ask for an assignment, true assignment, such that at exactly 1 literal is true in the clause. You don't accept 2 literal to be exactly 1. Okay, this is the problem. And then this problem is incomplete as well. And then we did this reduction. It's very easy. Actually, we take we have supposed to have this formula, and then we create a node for each variable and this gadget for each clause. And then we use the blue and red here in this way, and blue and red here in this way. Actually, the blue means true for this clause, and the red false. Okay, and then we lie, and then we have to make the paths from S to T. And then we'll do like this. For example, V1 occurs in 2 literals, so I have I will join all the clauses that where the positive V1 occurs, and at the last one I will put an arc to T. The negation of V1 doesn't occur anywhere, so I put a direct path from V1 to T. And V2, the positive one is in C1, and the negative one is in V2 and C2, so I put two paths. Observe that I'm using a new color for each vertex. I have in this, I start the paths, and I complete using the same color. And the third, for V3, it occurs positively in C1 and the negation in V3. So I put two other paths in this way. And so I have 2 times n times, isn't it? If I have n variables, 2 times n. And if I have a solution such that I can split this flow, because again, what is the value of the flow? It's uniform. It's n value. It doesn't matter. But if I can split this flow in bichromatic numbers, so the formula, the answer is yes for the formula. And so I will ask if my flow is splittable, and with it, I have the cost of the decomposition will cost for n. If I have this, it's because I have 2 n paths, each one with 2 colors, only using 2 colors. And that look at this. If I take V1 as false, it means that I will take this red edge and come here, this red, and here this red edge. Nice. And if I take V2 to be false, so I will take this one red, and maybe it will be through here. So, the first one will be red, but in second one we'll take the blue path, the blue edge, and then the V3 through it will be, this one will be red. Again, it'll be blue, and the other one, which is negation, will be red. I don't know. But it's not hard to see that I can decompose only in bichromatic paths if I have a true assignment as required in the verb. Okay. And then maybe you are by now think that, okay, there are some positive results. And actually, not many, but okay, we proved that if I have, I will show a table by the end, but at least we have this positive result here. Actually prove that if I have a DAC, it's acyclic, and I have only 2 distinct flow values, but I'm not required one to divide the other, okay? We can solve this. So we are going to, I'm not, maybe not explain the algorithm, but to be, I use MDC, máximo divisor comum. Maximum common divisor. Okay. So I will take the values, I will see, okay, I can, I will take the maximum divisor common and send unities of this thing. I will create another network with multiples of this thing, and I will have only 2 values, and one divide the other, and I apply the other algorithms. And I will look at the remainder, and I will adjust with the remainder, and I will do several times, and it's solvable, actually. So I will do like this. So at the first step, I have I don't have paths with uniform with 7, having 7 all the arcs. But when I have 5, so I have 5 paths with 5. And then I will look, I will be left with this thing, because I use 5 from the 7, and those arcs weren't used. So I will take 2 and 4, and I will send as much flow as I can. I will have 4 paths in this configuration, and I will look at the remainder. I will have 2 and 1. and I have two more paths, so I can solve this in polynomial time. And so that's also on the two values, two colors. And so, actually, this is why I thought this interesting to bring this problem to you, because that's lots of things to do yet. So this is the table I need to make a resume of the situation, okay? So in here, it means uniform, only one value of flow. So it's polynomial in monochromatic graphs, but it's polynomial as well when I have only two colors. And we prove it, I show you, I gave you an idea, it is NP complete, even for DAX, isn't it? But if I have two values of flow, the only results are this. This result of Hartmann that says that if you want to divide the other, okay. And our result that says that if the network is a DAG, okay. But in general case, it's open, okay? If the network is N1 and the values of the flow is N1, and everything else is NP complete because, that's it. Yes, we have another result that is if we have any value flow, but the value matches with the color. I mean, all the colors have L and blue have as the same value of flow, and then we can solve as well. And then would be the open problems that I think they are interesting by the end. First of all, we didn't touch approximative algorithm for our problem. For the K-splittable flow, there are approximative algorithms. And it would be nice to look at FTP algorithms and approximative ones. And it would be nice also to determine the complexity of the flow decomposition for networks with any two values of the flow and the arcs. And then two colors, in the case they are colored, but with no match between colors and flow. Actually, as we have seen in our reduction, we need 5 colors at least. So it'd be nice to ask, what about acyclic digraphs, but with 3 or 4 colors? It would be NP complete as well or not? We don't have a reduction for this. And actually, remember that we define this, which will be our cusp of decomposition. So we have other definitions that would be nice to see as well. For example, in the first one, instead of minimize the number of colors in each path, I would minimize the number of components in the colors used in each path. And why this? Because sometimes you are sending a flow from a path from S to T, and suppose that when you change the color, you have some cost because you are changing the way you are sending things. And so maybe you have only 2 colors, but you are changing one by one. So it would be it would be nice. But maybe you have only 2 colors, but you have the first block of the path with 1 color and the second block of the path with the other color. It would be a better solution for some applications. So this problem, we have done nothing but defined about it. The second minimization, it's because you are maybe interested in have a balanced number of colors in each path. So maybe you have a solution, one solution use a monochromatic path, 1 color, and the other path will use 9 colors, for example. But maybe for some reason, for you, it's nice to have 5 colors in the first one and 5 colors in the second one. So we have the total cost in our version will be the same, but in this version will be very different. So in this version, actually, you want to have more or less the same number of colors in each path. And this last one will be very interesting. Suppose, okay, I'm spending lots of colors in this path, but I'm spending lots of flow in this path. So you want to see this relation between the amount of flow you are sent by a path and the amount of the colors you are using. And maybe you want to minimize this instead of only minimize the number of colors. Okay, so it will be this. I hope I'm still on my time. And I thank you very much for your attention. I ask if you have any questions. Yes, actually, it's to congratulate you because I was here during the parties of the independence, and they're amazed how you party well the independence. Nothing to do with Brazil right now, you know. So thank you for your attention.
And any questions or comments? Preguntas, comentarios. If you have a question, please raise your hand, and I will go to your place with the microphone because we're transmitting through YouTube. So.
Gracias. So, what about this duality with cuts? Are there any kind of cuts that interest you in your colored problems?
Actually, the cut with the less number of colors, it's an open problem. We don't know it. It seems to be very hard. Actually, it's not NP complete like the max flow. So it's very hard, and then actually it didn't work but under this point of view.
But
thinking about the cuts.
Yeah, and so there's no duality by saying if you find a cut with a certain number of arcs and a certain number of colors, that would say that the flows that you are looking for must be at least of some size or anything like that? No.
Oh.
That's a shame. And the second question, very quick. Are there any applications that you have considered for this? Because there seem to be.
Yes, many. In our imagination. Yes, because we are thinking that actually they are colored networks. They have, if you pick any of one of the previous paper that proved that the ST path, the minimum path is NP complete, or the flow max is NP complete, so they will enumerate lots of application of find flaws with a certain number of colors or minimize them. But actually, most of the problems, it was our imagination, but this is fundamental researchers like this, isn't it? We do something and maybe in decades after people will find some application. This is basic science, actually. It reminds me, Einstein, fortunately Einstein is there to remind us because he did relativity theory in the beginning of this century, and by the end of the century, we're using this in our GPS.
Okay, thank you.
Any other questions, comments? No? Well, in that case, thank you very much for your talk. It was
kind of you. Yes.
No, it was very kind of you to accept the invitation. And this is the place where we go back and forth. And so to stop the cycle, thank you.
Thank you a lot.
Y en 2 semanas tenemos otra sesión del Súmate, ya va a ser un tema diferente, el tema dentro de 2 semanas es fractales y educación, ¿no? Enseñanza matemática. Entonces están cordialmente invitados, sobre todo porque veo muchos rostros jóvenes, ¿no? Muchos rostros jóvenes. Entonces están invitadísimos y que tengan una muy bonita tarde. Ojalá nos veamos.